Good morning. I'm very excited to be here at the ERI Summit to talk about some recent work that we're doing in a program that we call Enabling Confidence. It's a very focused 18-month program. It's an artificial intelligence exploration program. So I'm just going to kind of jump right in. So the type of confidence that I'm talking about might be a little bit different than what you might be thinking. So in a statistical estimation chain, where we're trying to do something like, in this cartoonish example, identify friend and foe, ideally what we want is a sensor that outputs a signal that can be used to discriminate between the objects that we're looking at. And what we tend to do is we try to characterize that discrimination output very well. And you can see on the top case where we have this great separation in terms of this likelihood function, we can imagine making decisions that are critical to the mission relatively easily. However, in the bottom case, where there's a great overlap between these outputs and the likelihood, you might think it might be very difficult to. And that is generally the case. However, if you have a high degree of confidence in that likelihood function, and also in the error model behind that and how it may or may not be correlated with the errors in other sensors, then it makes a greatly different picture in terms of how you can fuse different sensors together to extract the maximum amount of information. For example, if you had 5 independent sensors where all of the errors were independent, you can imagine getting a lot more information than if they all fell victim to the same types of errors and their errors were all correlated. So enabling confidence is about trying to bring this type of methodology to machine learning systems. So what's the problem today with conventional machine learning systems? So typically we have things like deep neural networks that are processing sensor outputs. And you might think that we get an idea of the probability for classification of, let's say, a friend versus foe. However, these typical softmax type functions that one sees that we think of as probabilities really aren't. And even so-called calibrated softmax outputs are not probability distributions. So what is the difficulty here? So even in a sensor environment where we have a well-characterized sensor where we know the errors on the inputs, the nonlinearities in the neural networks tend to make it intractable to propagate these error models through the network to develop the output probability distributions, or you could think of it as cross-correlation coefficients for the errors in these. So enabling confidence is about 2 fundamental things. How do we generate that question mark in the lower right-hand side? And what are the computing resources that are required to do that? And this is where MTO comes in, because we look at the question of what new computer architectures might be required in order to do this in a feasible way in the battlefield. So I don't have time to go and even talk about the 9 performers and all the different ConOps that they are doing in this program. They're all doing great. I only have time to present one example that I think I can explain in just a couple of minutes. And this is from Science Technology Research Corporation, where they're using Doppler radars as their input sensor. So we have an airplane that has a Doppler radar. And what that generates, if you're not familiar with it, is shown in this Doppler range map picture, which is a 2-dimensional image that shows range and range rate for all of the scatterers in the field of view of the radar. And so the system that they have in the middle has an ML system that generates estimates for the range and range rate for the different individual scatterers. And what they're doing in the Enabling Confidence program is also developing a module that generates the output uncertainty probability distributions for this sensor. And the idea is that both of these can be fed into a statistical hypothesis estimator so that we can do multi-object tracking more efficiently. So how are they doing? So here is an example of one of the output uncertainty distributions that they have come up with. It might be hard to see the exact nature of it. However, it is a 2-dimensional quasi-Gaussian-like distribution. The color indicates how well they're doing relative to the ground truth for this sensor system. So blue is good, red is bad, and you can see where the predominant amount of energy is in this system. They're actually doing very well. So we're very optimistic that we can generate these output distributions. And now we have to do the next step of feed them into the statistical estimator. One of the things that we're trying to enable with this is look at enabling a concatenation of systems in order to take a very complex battlefield environment and raise human interaction to a higher level. Thank you very much.